Let's prove that every group of order 15 is cyclic. This is a special case of a beautiful pattern. Whenever P and Q are primes with P not dividing Q minus 1, every group of order PQ is cyclic. Let's see why it works for 15. Let G be a group with order 15. Note that 15 factors as 3 times 5. By Cauchy's theorem, which guarantees that prime divisors of the group order always show up as element orders, since 3 divides 15, there exists an element A in G of order 3. Similarly, since 5 divides 15, there exists an element B in G of order 5. Let H be the cyclic subgroup generated by A. Then H has order 3. The index of H in G is 15 over 3, which equals 5. Now, here's a key theorem from the theory of group actions. If the index of a subgroup equals the smallest prime dividing the order of G, then that subgroup must be normal. This is proved using the permutation representation on cosets. We'll take it as given. So let's try to use this. The smallest prime dividing 15 is 3, but the index of H is 5. 5 is not 3, so our first attempt hits a wall. The theorem doesn't apply to H, but don't give up. Instead, let K be the cyclic subgroup generated by B. Then K has order 5, and the index of K in G is 3. And 3 is the smallest prime dividing 15. Therefore, K is a normal subgroup of G. Now, since the orders of H and K are 3 and 5, and GCD of 3 and 5 is 1, H and K intersect only at the identity. Any element in both would have order dividing 3 and 5, hence order 1. By the product formula, the size of HK equals 3 times 5 over 1, which is 15. That's the entire group. So G equals HK with trivial intersection and K normal in G. Now, here's the key move. Since K is normal in G, conjugation by elements of H defines a group homomorphism from H into the automorphism group of K. K is cyclic of order 5, so its automorphism group is cyclic of order 4, since each of the 4 non-identity elements can serve as the image of a generator. H has order 3, and the automorphism group has order 4. For a homomorphism from a group of order 3 into a group of order 4, the image must have order dividing GCD of 3 and 4, which is 1. So the homomorphism is trivial. Conjugation by any element of H does nothing to K. In other words, HK equals KH. Every element of H commutes with every element of K. Notice this argument depends on 3 not dividing 4. If we tried this with a group of order 21, we'd have aught of Z mod 7 with order 6, and 3 does divide 6, so the argument breaks. And indeed, non-abelian groups of order 21 exist. Now consider the element AB. We've just shown that A and B commute, and their orders 3 and 5 are coprime. By a standard result, when 2 commuting elements have coprime orders, the order of their product equals the product of their orders. So the order of a B is 3 times 5, which is 15. So a B generates all of G, which means G is cyclic. Let's recap. We used Cauchy's theorem to find elements of order 3 and 5. The index smallest prime theorem told us the order 5 subgroup K is normal. Then, since the automorphism group of K has order 4 and 3 doesn't divide 4, conjugation by H must be trivial, so H and K commute. Finally, coprime orders gave us an element of order 15, making G cyclic. And that completes our proof.